We'll take on a slightly less dense topic. Density. I'm going to get some more dense stuff. So charge density. All right, and you're going to see charge density played a pretty important role in this entire derivation. All right? And, okay, before we move on, are you guys following what we did here? Yeah. We're going to do a couple more of these examples before I throw you out to the homework, but this is this kind of technique will 100% be on the first test. So if you're not getting it, make sure you ask some questions. Yes?
That limit, was it x times L over 2 or x to the power of L over 2?
X times L over 2. It looks new and terrifying, but it just takes practice. Okay. All right. So let's talk charge density. So linear charge density. Remember, there's 3 different kinds of charge density. They depend on the dimensions of your object. Okay. Linear charge density, what dimensional object is that? 1. Okay. It's charge over length. All right. So linear charge density, total charge over total length. We call it lambda for whatever reason. Surface charge density, guess what that is? Charge over surface area. Okay, so if this thing has an area A, you smear a charge Q over it, what do you think the surface charge density is? Q over A, all right? And it's either called eta or sigma. Those are both Greek letters. Neither one is fun to write or remember. Depending on which book or video or whatever you're watching, some people call it eta, some people call it sigma. Eta is this sort of weird N, and sigma is like a backwards 6. Okay. All right. What other kind of charge density would you expect there to be?
Volumetric.
Volume charge density, which is just Q over volume, which is V, and it's represented by the rho that we use for mass density. Okay, so here's a question. And we'll take a minute and a half. Okay, we are pretty sure it's not A. Please discuss, we'll vote again. Okay.
It's not air.
Let me pose a. I'll be right back. This requires a demo.
Yes, I wasn't sure about that. Because I think it says this one, but so there's not a charge.
We have what?
Yeah, that's going to start that. Do that later on. Yeah, I think it's like but if we're
You can't hit it from the arm.
as long as you can make this up, it doesn't have to have something like they're gonna be like co-authors and structure.
Okay. So here's an analogy. What's the density of water? One-ish. Yeah, 100 grams per centimeter cubed, or 1 gram per centimeter cubed, yeah. So if I pour water in this, and then I pour some of the water into this, and maybe more of this, what's the density of water? Has it changed? Okay, what's the density here? N sub A. Okay, if I break it in half, does it change the density of the object? No. Okay, so the answer is E. Alright, and that was the key here too. Right? The density of this thing is Q over L. The density of a little chunk of it is still Q over L. The density of half of it is still Q over L. Okay, just because we use the whole thing to get the density doesn't mean the density changes. If I break the desk in half, both halves have the same density as the whole desk. Okay? Here's what I think you thought was happening. Yes, that's better. We're not going to re-vote. This is going to be this. Remember, these things all have uniform density. So the biggest one should have the most charge, and the smallest one should have the least charge. And it's based on the size of the objects. We're talking about charge, not density. Okay? Density is the same no matter what. Charge changes based on the size of the object. Okay? All right. So we're going to try a problem. Okay, so first try this on your own. There's two key principles we have to remember. The first is that the surface charge density is just Q over A. And the second is that we know that for a conductor, as soon as charges are on there, they distribute pretty much evenly. So as the two-dimensional space, we can assume that the charges go all the way evenly over the surfaces, which is not totally true, but good enough for doing this problem. So let's start out with metal sheet 1 and metal sheet 2. So metal sheet 1 is a little bit smaller. Okay, so it has an area 1 of 2.5 times 2 meters, so that's going to be 5.00 meters squared. And then it has a charge of 4 coulombs. Okay, so that means the surface charge density is going to be Q1 over A1, which should be 4 over 5, giving us 0.8 coulombs per meter squared. Okay. We also have this number 2, which is 5 by 3, so a little bit bigger in both dimensions. That means the area 2 is going to be 15, and charge 2 is 10 squared coulombs. So that means our surface charge density for 2 is Q2 over A2, and that's going to be 10 coulombs over 15 meters squared, which is equal to 0.67 coulombs per meter squared. Okay, so that's what we're starting out with. However, when they touch, and I'm going to shrink this down a little. When our two sheets touch, now we have sheet 1 and sheet 2, and they have a total surface area and a total charge. Okay, the charge distributes equally, so it doesn't really matter how it's structured. So that means A12 is going to be 20 meters squared, and Q12 is going to be 15 coulombs. So our new surface charge is just even, because remember, it's distributed evenly. So that's going to be, oh sorry, not 15, it's 14. 10 plus 4 is 14. Okay, so that's going to be 14 coulombs over 20 meters squared, giving us 0.7 coulombs per meter squared. So that is the charge density that we're dealing with now. And in order to, if we separate them again, and assuming they stayed evenly distributed, because that's a good assumption for conductors, now we have the same areas, but we have different charge densities. And so we just take this equation and we rewrite it so that we get this in terms of charge. So charge is going to be this density times area. So charge 1, we'll call this charge 1 nu, is going to be nu times area 1, and that's going to give us 0.7 coulombs per meter squared times area 1, which was 5 meters squared, and that gives us 3.5 coulombs. Try to write that better. And then Q2 nu is going to be nu times area 2, and that's 0.7 coulombs per meter squared times area 2, which is 15 meters squared. So that gives us 10.5 coulombs. So here's our nu Q1, here's our nu Q2, and just to check, these still have to add up to the same amount of charge because you can't just lose charge. And so before we had 14 coulombs of charge, and if you add 3.5 plus 10 point, oops, that should be 10.5. 10.5. 3.5 plus 10.5, you should still get 14. So that's a good check. So we got the surface charge density of each thing. So that's N1. We also got N2. We found the new surface charge density. And then we used that to get our new charges when we separated our sheets again. So going back to this derivation we just made, all right? We're going to discuss this. We will vote again. All right. Oh, good. Let's see. C is the correct answer. Okay. But let's go through these. If you make the rod longer without changing the charge, what happens? It gets weaker, right? You diluted the charge density, so you're not going to have a strong field. What about making the rod fatter without changing the charge? Kind of the same thing, right? The density goes down. You're moving some charges a little bit closer, which will make that part of the field stronger, but you're also moving charges farther away. And remember, for each charge, it drops off like inverse squares, so those will stop contributing pretty much. This one is the right answer. You're changing the charge density. You're making it more dense without taking anything away. So that's obviously going to be the correct answer. And then removing charge from the rod, obviously a stupid answer. Moving the dot farther away, obviously made all the R's longer. That's